instead of going over the homework tomorrow in class, so we could squeeze in some more challenge problems, I thought I can put the solutions online here in a video, and you guys can just kind of scroll through the video if you need to. You can kind of see what the answer is. You know, as you're fast forwarding through the video, if you realize that you missed a problem, then just rewind it back and watch the solution. Typically, I'll try to do a problem maybe 1 or 2 ways. I don't want to make the video too long by doing like 4 different ways to do the problem. So I asked a friend of mine to come help me. I was reading one of his books last night to my daughters, and I thought, you know, he would be an excellent use. He probably also needs to learn a little bit more math and some geometry, because I think all he basically knows to do is to count to 10. So I brought my friend Elmo from Sesame Street. He's going to help us out.
Hi, Mr. G.
Hey Elmo, what's going on?
I'm pretty excited to learn about this geometry thing.
Like, well, have you been paying attention at all with what we've been doing?
No.
You're probably going to be lost. So, but that's okay. We'll get through this thing, Elmo. Anyway, here's the first problem.
What kind of shape is that?
It's called a trapezoid, Elmo.
Trapezoid. This is my song. La 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 la.
Elmo. Shh, shh. It's okay, buddy. We'll get through this. Okay. Trapezoid, we could use some formulas here. We could use 1/2 times height times the sum of our 2 bases.
Hey, that's a nice red color.
Thanks, Elmo. Thanks. Switch to blue now.
Hey.
So we could use this formula. We can see here. Now, it's a question that you might have is the 15, is that all the way across there, or is that just partially across? Well, if I see the 11 up above, I would venture that if I were to drop down the other height over here on this end, then this much would just be 11, which would make this other leftover piece 4. Okay, but I don't think we're going to need to go that far. So yes, 15 goes all the way from here to here, and this is how it would get split up between 11 and 4. So our entire bottom base would be 6 plus 15, which would be 21. Our top base up here is 11, so we could go ahead and fill in those 2 pieces. And the only thing we're missing is the height. So the height would be right here. We can use some trig because we have a right triangle. We have the opposite. We have the adjacent. And so we could use tangent. So we'd have tangent 60 equals opposite h over adjacent 6. This is a multiplying problem. So we multiply, and 6 times tangent 60, according to my calculator, is 10.4. And there's our height. So now, if we do 1/2 times 10.4 times the sum of our 2 bases of 21 and 11, makes 166.4 millimeters squared. So Elmo, was that a pretty easy problem?
Dude, you are totally losing me. I think I might go play with my friends.
Where are your friends at?
Sesame Street? Duh.
Oh, yeah. Oh, well, you want to stick around a little bit longer?
Yeah, maybe for a couple more problems.
Okay, but the next problem's not going to be, well, here, what's after 9, Elmo?
10.
Hey, that's what problem we're doing next. Sweet.
Yay!
Except you'd still bomb this test, Elmo. I'm sorry. All right, number 10. They didn't tell you this thing's a rhombus, but it is a rhombus. There are some additional markings, like really these 2 sides should also get the 2 arc marks here. And this piece and this piece are also congruent. And on the test, I will have those things on there. Now, the diagonals are perpendicular, so really we have 4 right triangles going around here. If we wanted to use the formula 1/2 d1 times d2, well, we know what one of our d's are, which is 16. That would be this 8 plus 8 piece here. But we need to figure out the length of this other diagonal. Now, to figure that out, one thing I notice is, number one, I don't have angles present, so maybe I'm not going to use sine, cosine, tangent. But I do notice that with each one of these right triangles, I know 2 of the 3 sides. And so I know the 8, I know the 10, and the one piece I don't know, which I'll call x, which means this piece up here is x. Um, this is one of those special Pythagorean triples. This is a 6, 8, 10. It's really a 3, 4, 5 in disguise. So that whole other diagonal is now 12. And so 1/2 of 16 times 12 makes 96 feet squared for our area. Now, if you don't want to use the formula, you could just find the area of, say, this triangle right here. The base and the height are perpendicular, which means the base and the height must be the 8 and the 6. So the area of one triangle would be 1/2 base times height, which would be 24. And we have 4 right triangles, which makes our 96 square feet.
But my feet aren't square.
Ah, good God, Elmo. Next up, 21.
Hey, 21's not after 10.
Oh, Elmo, someone's gonna go to puppet heaven soon.
Snuffleupagus?
Why, what's wrong with Snuffleupagus?
He's not doing so well.
Oh, sorry. Bad joke. Anyway, a regular hexagon. Let's get a regular hexagon here. Here's a regular hexagon. Doesn't quite look like our stereotypical hexagon, but if I do a little rotating, boom, there it is. The apothem is 6. Now, from our center, all of the lines that we would draw out, those were our radii. Now, we don't know what those are, but one thing we did talk about being special about a regular hexagon is that all of our triangles are equilateral. So every one of these pieces gets a congruent marking. Now the apothem is our height in each triangle. So there's our height, very poorly done, which is 6. Now, we could try to use side angle side if we knew what the radius was, but since we know the height, we could try to figure out what the base is. Now, is the base also 6? No, it is not 6. So here's what we could do. We can take our 360 divided by 6 triangles, which makes 60 degrees, but we cut that 60 degrees in half, and so there's 30 and 30. So now I'm going to figure out this much of my base, and so I'd want to use, tangent 30.
Oh, there's the red again.
Elmo. Oh, buddy, you're going to die. Opposite over adjacent. This is a multiplication problem.
Did you say I was gonna die?
No, Elmo, I said you're fantastic. 6 times tangent 30, let's see. 6 times tangent 30 is 3.5, which means our other little piece down here is also 3.5, which means our base is 7. So now we can go ahead and find the area of one of our triangles, which is 1/2 base times height, which would be 7 times 6, which makes 21, times 6 triangles altogether, and there's 126 square inches. Now, if you wanted to call, say, the hypotenuse y, or really, why would we call them y when we could call them r because they are radii, you could use, cosine of 30 and figure out what the radius is, and then use side angle side with that number, the 60 altogether, and another radius. But then you'd have to multiply that by 6 as well. So many different ways you could do this problem. You find one way that works for you. 22.
Hey, you're back on track again.
Yes, Elmo, 22 is after 21. Regular quadrilateral, aka a square, like Elmo.
What does that even mean?
Can't tell you, buddy. So, radius, let's draw one of those in. There's a radius. Okay. There's another radius. Okay. So that's 2, that's 2. Now here's the type of example of where we might want to use the side angle side shortcut, but we need to know how big is that angle in between the 2's. Oh, too much there. There we go. So if we do 360 divided by 4, we get 90, and hey, that is a 90-degree angle right there. Now, before I mentioned from time to time that using 90 degrees with sine, cosine, tangent really wasn't a great thing, but it's okay with sine. Cosine and tangent, not so much. Occasionally cosine 90 is okay with the law of cosines. Tangent's never okay. You will end up getting a domain error in your calculator. So let's do side angle side triangle, which is 1/2 side times sine of the angle. So our sides are 2 and 2. Oh, I meant to put A there instead of 90. And the sine of 90 is just 1, so really I get a big whopping 2 out of this. So this has an area of 2, and there's going to be 4 triangles inside this square, so the area is 8 meters squared. Now, something else we could have done was the Pythagorean theorem, because hey, this is a right triangle, and we need to figure out the hypotenuse. Well, here's one of those patterns that come into play where if the two legs are the same number, the hypotenuse is that number with a square root of 2 attached. So really we have a square that has a base and a height of 2 root 2. We'll leave that. So we could just say area is base times height. Base is 2 root 2. Height is 2 root 2. So now 2 times that 2 makes 4. And root 2 times root 2 makes 2, which makes 8 altogether. And so there's another way we could find the area of that square. 23.
Yay!
One thing I notice here, I have a triangle, and hey, there's a side angle side. So it would be preferable, I mean, quick and easy, if we use the 1/2 side times sine of the angle. And that is going to find the area of the whole triangle there. So now 1/2 times 19 times 15 times the sine of 45 is approximately 100.8 centimeters squared. Now you might ask, Mr. G, what if I forgot that side angle side shortcut formula? Well, you could always drop down a height. There's our height. And you could use the 45 to figure out the opposite side when you know the hypotenuse. And hey, guess what trig ratio we're going to use? Sine. And so you could just do that, figure out the height, and then use the base of 19. But what you'll find out in the end is this. The height of the triangle is whatever 15 times the sine of 45 is. Okay, here's our 1/2. 19 played our base, and all of this represents the height. And there's basically 1/2 base times height. Next up, 22.
Whoa, you're going backwards.
I am, Elmo. Good eye. A couple is taking a balloon ride. After 25 minutes aloft, they measure the angle of depression from the balloon to its launch place as 16 degrees. They are 180 feet above ground. Find the distance from the balloon to its launch place. So, we need a balloon. Here's a balloon. Here's the basket for the balloon.
A basket for a balloon? Who said you could ride in a balloon?
Elmo, I don't think it's such a great idea for you to be on the show today, buddy. You drive me crazy. Here's a balloon. Here's our couple. Yay, they're waving at us. Hi. What do we say? Angle of depression. So here's our launch place. So let's say here's where they took off from. Launch. And so the angle of depression, first, they're looking straight ahead. And then they look down from the angle of depression. Here is our 16 degrees. They are 180 feet above the ground. Well, from here to here would be the 180, but we could also put that over here. So if they were just to have went straight up from the launch pad, they would still be 180 feet up in the air from there. Okay, now where does our x belong? Find the distance from the balloon, here's the balloon, to its launch place. Here's the launch place. Connect the dots. Really, we're right there. So here's x. Here's our right angle. Now we can use our 16 degree. Here's the opposite. Here's the hypotenuse. So we're going to use sine. Sine 16 equals opposite 180 over hypotenuse x. This is a flip-flop problem.
Ooh, I like wearing flip-flops.
Elmo, you don't even wear shoes. Just, oh my gosh. So 180 divided by sine of 16 is 653 rounded, this said, to the nearest foot. So they are 653 feet. They have floated in the air to where they currently are. And the last problem, 24.
Hey, you skipped 23.
I'm counting by evens, Elmo. Counting by evens here, buddy. 7. Oriana is flying a kite. She lets out 105 feet of string and anchors it to the ground. She determines that the angle of elevation of the kite is 48 degrees. Find the height the kite is from the ground. So, Elmo, I'm going to put you in this problem.
My name's not Oriana, though.
I'm aware, but you're going to be on the kite.
Yay, I get to fly a kite.
No, Elmo. You're not going to fly the kite. You're going to be on the kite. There's Oriana.
Okay, hi, Oriana.
Let's give her some hair. Oh, Oriana, she's so beautiful. She's so happy. She's flying her kite. She's not really flying the kite. She just anchored it to the ground. What weirdo kid anchors a kite to the ground? Anyway, there's our string. Here's our kite. Okay, you ready, Elmo? You ready to be in the problem?
Okay, but where am I going to be?
Elmo, you're on the kite. There's Elmo. I hope you're ticklish up there, buddy.
I don't like heights.
Tough luck, buddy. Tough luck. There's 105 feet of string.
I'm getting scared up here.
Just close your eyes, Elmo. Wind's blowing pretty strong. It might float you away. Who knows? Angle of elevation, 48. So first, Oriana, if she was on the ground looking, she'd be looking straight ahead, and then straight up at Elmo, who is scared beyond belief up there.
Oh, help me!
And there's our 48-degree angle of elevation. Find the height the kite is from the ground.
I'm scared up here. Get me down.
Elmo, as soon as the wind dies down, you'll fall straight down to the ground.
How far am I going to fall?
That's what we're solving right now. We'll get back to you. So here's our 48-degree angle. Here is the opposite side. Here is the hypotenuse. So once again, we use sine of 48 equals opposite x over hypotenuse 105. We have a multiplication problem, so we multiply both sides by 105. And so 105 times the sine of 48 makes to the nearest whole number 78 feet. Elmo's going to drop from the ground.
No, I die at 60 feet.
How do you know that, Elmo? How do you know that at 60 feet you're okay?
I was in a bad accident one time.
Well, I'm sorry, Elmo. So Elmo stuck up on the kite. Hopefully that kite's going to be up there for a while. So that is all. I hope you got something out of that. I hope you had a little fun. And we will see you guys tomorrow in class.
Bye, everybody.